Okay, in this section, this is a really good section because it summarizes everything we've done so far with series. If you understand this section, you pretty much understand everything we've talked about. And anyway, so putting it all together is kind of important. When you're trying to see if a series converges or not, the question is, what should you do first? Well, here's what I would suggest: ask yourself. First question I would ask is it easy? Is this are you looking at a geometric series or a p-series? If so, you know that a geometric series converges if the absolute value of r is less than 1. P-series converges if p is greater than 1. Maybe it's not a geometric series or p-series, but maybe you could compare it to something like that. It's amazing how helpful the comparison tests are. Maybe you can make it greater than or less than a convergent or divergent p-series. And then another one would be look at the nth term. You could do this first actually. Does the nth term of the series go to 0? If it doesn't, then you know that you have a divergent series. But remember, just because the nth term goes to 0 does not mean that it converges. Think about the harmonic series. If the nth term of the harmonic series goes to 0, but it still diverges. So, but if the nth term does not go to 0, you're done. You can stop and say the series is divergent. If you're lucky enough to have an alternating series, and all you're asking is the question, does the series converge? Then you could jump right to the alternating series test. You look at the b sub n's, and you want to make sure that's a monotonic decreasing the b sub n's. And you also look at the limit as n goes to infinity of the b sub n's. If the limit is 0, then you know you have a convergent series. The only thing with alternating series is, you know, it could be conditionally convergent as well. So if the question is, does the series converge absolutely, conditionally, or diverge, I wouldn't jump to the alternating series test. I would first look at the absolute value of these terms and see if it's absolutely convergent. If it's not absolutely convergent, then I would go to the alternating series test. Again, that's if I'm asking the question if it's absolutely convergent, conditionally convergent, or divergent. But if the question is just, does it converge, you can jump right to the alternating series test. If you have factorials or constants raised to powers, you might try the ratio test. If you have expressions raised to powers, you might try the root test. And the integral test, don't forget about that. If the integrand is easy to integrate, you might have some luck with that. Okay, so in these first problems, all we're asking is the question, does the series converge or diverge? So think about what I just said and see if you can determine that. See if you can pick the right test and see if you can decide if these are convergent or divergent. Hit the pause button. Okay, in this first one, you should have used the root test. I would have suggested that one because you have things to powers. When you take the nth root of this, I think it cancels the nth root cancels with this n, and you just have this, right? And the limit here as n goes to infinity is just 0, which is less than 1. So by the root test, the series is convergent. In fact, this is absolutely convergent, right? A positive term series, you could also say, is absolutely convergent because the absolute value of these is just the same terms, right? But that's not the question. The question is, does it converge? The answer is yes. This next one, how would you handle this? Okay, here I would have tried the ratio test. It's kind of messy, but let's look at the a sub n plus 1 ratio over a sub n. This is your a sub n. So what would a sub n plus 1 be? You replace n with n plus 1. You see the parentheses around the n plus 1? You have to do that. This right here is a sub n plus 1. You replace n with n plus 1, you get this. And when you replace n with n plus 1 here, you get n plus 2 factorial. This is not a sub n. This is the reciprocal of a sub n. So that's just a nice shorthand way to write it. Now there's a lot of stuff that I left out here. You see that n plus 2 factorial is equal to n plus 2 times n plus 1 factorial, right? So if you write n plus 2 factorial as n plus 2 times n plus 1 factorial, you can actually cancel the n plus 1 factorial with the n plus 2 factorial, but you have an n plus 2 left on the bottom. That's where this came from. And the only other thing I did was, I took this is 2n plus 2 raised to the n plus 1 power. I took off one factor of 2n plus 2. So I pulled off one factor of 2n plus 2. Notice this becomes 2n plus 2 just to the n power. So this, the product of these two factors equals this right here. Okay. And then what I did was, I'm taking the limit now of this. It's kind of a mess. I apologize for that. This is 2n plus 2 over 2n to the n power. I know this limit is going to be 2. What about this limit as n goes to infinity? Over here I did that work. You see I call this y, and then I took the natural log of y. We've done this before. So I'm going to apply L'Hopital's rule to this, but first I have to write the 1 over n in the denominator like this. And then I apply L'Hopital's rule. What you get is you take the derivative of the top, which the derivative of the natural log of something is the reciprocal of it times the quotient rule. You get the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Kind of a mess, isn't it? So anyway, when you simplify this though, when you simplify this, I think you just get -4. Okay, this numerator becomes -4. See this 2n? That cancels with one of these two n's. So you have a 4 over here, a -4 I should say. You have a -4 here, a 2n on the bottom, and you have a 2n plus 2 here. So this is what this simplifies to. And so the whole limit's 0, so the e to the 0 is what we're looking at, right? The limit of y would be e to whatever this is. So all this turns out to be 1. So getting back to the problem then, this limit's 2, this limit's 0, so the product is 0, which is less than 1. Therefore I show by the ratio test the series is convergent. That's a lot of work, huh? Let's try another one. Alright, how about this one? Okay, here, since it's an alternating series, and we're just asking the question, does it converge? Then let's jump right to the alternating series test. Let me just throw this in. If I ask the question, does it converge absolutely, conditionally, or diverges, I wouldn't jump to the alternating series test. I would first answer the question, is it absolutely convergent? Because if you can show it's absolutely convergent, then you don't have to worry about the alternating series test. But the question here is just, does it converge? So in that case, I'm just going to go to the alternating series test. B sub n is what you get when you take the absolute value, or you just get rid of the alternating part. So B sub n, they're positive terms. So what is B sub n plus 1? That would be 1 over n plus 5. And that's obvious that 1 over n plus 5 is less than 1 over n plus 4 since the denominator is bigger. So I just showed that B sub n plus 1 is less than B sub n. And the limit as n goes to infinity of B sub n, that's obviously 0. So that's all I had to show. I had to show B sub n plus 1 less than B sub n. The limit as n goes to infinity is 0. So by the alternating series test, it converges. It turns out, if you're curious, this actually converges conditionally. You know why? It's because if you look at the absolute value, you could compare the absolute value with 1 over n using the limit comparison test, and you could show that that diverges. So, but that's not the question. The question is, does it converge or not? And the answer is yes. Excuse me. All right, let's try another one. How would you handle this one? The bottom is basically, isn't the bottom basically n to the 3/2 power? So that's not right. The bottom is basically n squared, because when you have the square root of n squared, it's just an n. So you have an n times an n, you get 1 over n squared. So I'm going to use the limit comparison test with, excuse me, I'm going to use the limit comparison test with B sub n 1 over n squared, because that's because the sum 1 over n squared is a convergent p series. So you take the limit as n goes to infinity of B sub n. I have a sub n over b sub n. When you divide by b sub n, don't you just get n squared in the numerator? That's okay, you can do that. So when you take the limit, you could apply L'Hopital's rule. This time I'm going to do what a lot of students like to do. Instead of using L'Hopital's rule, they just divided top and bottom by n squared. That's okay. So on the top they cancel, you get 2. On the bottom, this n squared, one of the n's cancels with this n, the other n gets moved inside the square root, and that's why it's an n squared, because you move that n inside the square root. So then you divide each term by it, and you get this. So when you take the limit as n goes to infinity, you get 2, which is greater than 0. Remember, as long as you get a number that's greater than 0, using the limit comparison test, it's convergent. All right, this last thing I want to do here. Now we're asking the question, does it converge absolutely, conditionally, or divergent? So if you happen to encounter a alternating series here, you should first look at the positive term series and see if it's absolutely convergent. In fact, here it is. Here's the exact same one we just did before. Now I'm asking the question, does it converge absolutely, conditionally, or diverges? So you first of all, let's see if it's absolutely convergent. Well, it turns out, I think you can tell it's not, because this looks like 1 over n, so I'm going to use the limit comparison test. The series 1 over n is a divergent harmonic series. Don't say this is divergent. It doesn't make any sense. The series 1 over n is divergent, right? So by the limit comparison test, I'm going to look at a sub n over b sub n. When you divide by 1 over n, that's where that n came from. And the limit's 1, which is greater than 0. Therefore, I showed that it's not absolutely convergent. That's really all I can conclude right now. It's not absolutely convergent. It still might converge. In fact, it does converge. By the alternating series test, and in problem number 3, I showed that it converges. So here we go. If it's not absolutely convergent, but the series still converges, it's conditionally convergent. So let me say that one more time. If you're asked to determine whether an alternating series is absolutely convergent, conditionally convergent, or divergent, first determine if it's absolutely convergent or not. If it is, you're done. If it's not, then jump to the alternating series test and see if it's conditionally convergent. A couple more. Why don't you try these? Try this one. I'm just going to hit the pause button, then I'll show you the answer. How about that? I won't say a thing. This is what I got. I showed, the question, remember, is it absolutely convergent, conditionally convergent, or divergent? By the way, this is not a positive term series, is it? Some of these signs are negative. But if you take the absolute value and compare it with 1 over 2 to the n, you can show that it's absolutely convergent. Okay, how about this one? Something about this seems strange. Look at the denominator. Isn't the denominator always between 1 and 3? Right? Yeah, so if the denominator is always between 1 and 3, the whole thing is always between 1/3 and 1. I'm sorry, the nth term is not going to 0. Since the denominator is always less than or equal to, what is it? Is that right? Let me see. Yeah, the smallest this can be. Here we go. The smaller this can be is when the denominator is as big as possible. So the biggest the denominator can be is 3. So therefore, this whole thing is always going to be greater than or equal to 1/3. The nth term does not go to 0. It diverges. So look out for this. Okay, this last one is kind of hard. Let's go over this one together. This, again, it's hard to understand what it's even saying. I would probably go with the ratio test here. And look at what this means, okay? If you look at the an plus 1 term, I'm going to look at the ratio test, but what is a sub n plus 1? I replace n with n plus 1. So you see that 3 times the quantity n plus 1? And I replace n with n plus 1 here. You see 2 times parentheses n plus 1 times n minus 1. And when you write these out, the last term is, the last factor is 3n plus 3. Guess what the one before it was? Well, notice how the factors increase by 3 each time. So the factor that comes right before this is 3 times n plus 1. I should say 3n. That's not right. It's just 3n. The factor that's 3 less than this is 3n. And the factor that comes before this one, since they're odds, would be 2n minus 1. So if you write it like that, it helps. But you might have to stare at that for a while. This is a nice way to think of it. So when we look at the ratio then, what is the limit of the ratio of an plus 1 over a sub n? Well, look, I just got through saying this is a sub n plus 1. Now what is a sub n? It's the reciprocal of this, right? Now if you look very carefully, these guys right here all cancel with those, and these guys all cancel with those. So what do you have left? You still have a 3n plus 3 on the top and a 2n plus 1 on the bottom. And so we're using the ratio test, right? So this is clearly the limit goes to 3/2, which is greater than 1. Oh no, barely. But if it's greater than 1, that means that the series diverges. Well, that's it. We're going to diverge now. We'll talk to you later. Bye-bye.